Hello everyone, I am Mattia Da Luca, a PhD candidate at the Gabriele D'Annunzio University of Chieti in Italy, where Professor Vittorio Cicciani is my supervisor, and I'm also a visiting scholar at the Heriot-Watt University of Edinburgh, where Professor Eric Mackay is my supervisor. Here I'm going to show you some results of my PhD project, which is related to the geological modeling and CO2 flow simulation at the basin scale in saline aquifer. But before to start, let me thank all of my co-authors which contributed to the project and that supported me in this research. Field-scale projects such as Sleipner or Questum have demonstrated the effectiveness of CCS in reducing carbon dioxide emission and safely storing CO2. However, to achieve the midterm objective or international agreement, it is crucial to implement CCS on a larger scale. This will require the need for suitable location where operation can be largely deployed, meaning that the geographical region could be interested by multiple injections. Therefore, it's imperative to fully understand the regional response of the storage complex, whether it is for risk assessment, regulatory compliance, or to evaluate the storage capacity and trapping efficiency. Sorry. In this work, we investigate the interplay and impact of factors such as the reservoir connectivity and heterogeneities to analyze the integrity and evolution of long-term storage of CO2 over hundreds to thousands of years at the regional scale, using as a case study the boundary sensor formation in the UK Southern North Sea, which has been selected for those activities. The study area covers approximately 9,000 square kilometers and includes 6 of the awarded carbon storage licenses in the UK, the most notable of which is the Endurance project, indicated by the label CS001, and evidenced by the dark blue polygon. This region relies on historical hydrocarbon knowledge, which is mainly focused on deep hydrocarbon discoveries, as observed by numerous orange and green polygon and the wells, the red dots, shown in the map. The region has also been chosen because of the proximity to onshore CO2 industrial emitters and for the existing infrastructure that could be fully or partially repurposed to serve this operation. So to do the study, all the analysis and interpretation were conducted using the publicly available seismic and wellbore data within and surrounding the study area, retrieved from the North Sea Transition Authority data repository and OpenGIS database. And to cover the gap in the central area due to a lack of public data, we used the 3D reprocessing of the Cavendish survey provided by an agreement with SLB. All the data were managed within Bitrel, while the CO2 flow simulation were run using the Eclipse 100 black coil simulator. As observable on the seismic section above, the study area is characterized by a thick Mesozoic to Tertiary sequence, including the lower Triassic reservoir of the Banter Sandstorm Formation, highlighted in yellow. Laterally continuous and hydraulically interconnected, this saline aquifer overlays the evaporatic interval of the Permian-Sextian Sol group in the pink polygon, which promoted the development of several salt tectonic structures. In particular, they are dominated by northwest trending ridges with local four-way tip closures, as observable on the map below. The map falls above the seismic resolution were observed mainly in the southern and northwestern sector, while the already known paleogene dikes which allowed the gas migration from the deeper sources are found in the northeastern area. In terms of stratigraphy, the Banter Sandstone is generally thought to be an almost continuous and homogeneous coarse-grained fluvial and aeolian sandstone facies, which is sealed upward by the interval of anhydritic shale, dolomitic and alite intervals of the Middle Triassic iceberg group, thus providing sealing confidence across the study area. Consistent with what observed in the adjacent entrance prospect, there is a fair to good reservoir quality, but uncertainties in the positional setting and the extension of low permabuffer persist due to limited sampling of the boundary interval. Several uncertainties affect the area, like faults interesting both the reservoir and seal or the Paleogene dikes. Those elements provide structural weaknesses representing some of the main risk for storage containment. In this study, we focused our investigation on the uncertainty generated by the available pore space and the seabed subgroup of the reservoir. Prior to develop the simulation, a simple 3D grid with a 200 meter cell size and 20 vertical layers was created. The petrophysical model is based on the standard Gaussian distribution of measurement from 24 cores within the study area, indicating an average porosity of 0.19 and an average horizontal permeability of 35 millidarcy, while the vertical permeability is defined by a KV-KH ratio of 0.1. Due to a lack of the information on the depositional setting to investigate the possible impact of the reservoir heterogeneities in such an extensive area, we have reduced the KV-KH ratio to 0.01 in 2 layers. Simulation of 40 injectors distributed throughout the study area with an injection rate of 1 megaton per year per well for 50 years were run. The reservoir is modeled with a sterile pressure, and the injector are injecting from the 5th to the 20th layer. Almost 700 megaton of CO2 were injected over this period, and to simulate the safe injection, a bottom pressure limit of 75% of the lithostatic pressure has been applied, as evidenced by the figure 5b, which show the injection rate. Only the injector number 6 is affected by the pressure limit. Then the simulation has been observed for 5,000 years after the cessation of injection. To investigate the reservoir connectivity, the different scenarios of boundary condition were evaluated. Here I present the connected scenario. So in other words, with outflow at the boundary. Looking at the CO2 saturation, figure 4a and b, we can observe that during the injection period, the plume is migrating around 2 to 3 kilometers farther from the injection well, depending on the vertical and lateral heterogeneities. Then we will observe a movement of the highly saturated plume happening in mostly the first 1,000 years after the cessation of injection, and subsequently most of the movement is related only to the tail of the plume, because most of the mobile CO2 is trapped beneath the closure. So with this geological setting and injection rate, the CO2 will be entirely contained below the identified traps. Regarding the pressure results, the boundary condition will generate notable differences. As already said, we are observing the case with the outflow at northwest of Endurance site and at the seabed subgroup. You can clearly understand those 2 points by the on the figure 4c at 15 years, where the pink purple color is evidenced. So a constant pressure buildup is observed during the injection period. observable clearly in the plot on figure 5E, F, and G, which is mainly discharged in the first 10 to 20 years after the cessation of injection. So due to the open boundaries, a sustained gentle pressure release occurs in the following thousand of years, allowing the pressure to completely dissipate after 5,000 years. This pressure evolution is clarified by the profile, as I was saying, which clearly highlight the effect of the aquifer connectivity, especially in the profile cross-cutting the seabed subrock, where the opening boundary will allow to dissipate pressure and avoiding any kind of pressure buildup. Also, from plot 5a, we can observe that this pressure dissipation will generate a continuous outflow of displacement of brine at the seabed, which is indicated by the blue line. To conclude, we can summarize the main observation as follows. So it is critical to fully understand the regional and long-term response of the storage complex due to pressure interference generated by the injection activities. The plume migration occurs at the rate of decades and centuries, as shown from by the simulation, and the geometric configuration will define the containment capacity and efficiency, providing high storage competency of structures such as four-way deep undecline that we find in the area. The main driving forces of the system are subdivided in the viscous force is mainly affecting the leading the migration during the injection, while the gravity or buoyancy force is leading the plume migration after the cessation of injection, prompting leading the plume to migrate toward the top reservoir structure. The pressure will take thousands of years to return to the initial conditions, leading to a continuous brine displacement at the seabed and providing uncertainties in the activation of geological weakness. Furthermore, the long-term release generates pressure gradients controlling the reservoir in the flows. All those points generates uncertainties in the entire region, requiring to fully understand each part that is connected to the reservoir. Thank you for watching my presentation, and if you have questions, you can contact me by emails or just scanning the QR code. Finally, let me then express my gratitude to the Energy Simulation Board for funding me, for funding some of the international conferences I've attended during my PhD. Also, thanks to SLB, Segal, and Matal for providing academic software licenses which facilitated the work. And I'm extensively thankful to SLB for providing the Cavendish survey, and to Professor Bignardi for helping with the code developed to analyze the pressure data.